Okay, Assalamualaikum, a very good day to all. So we are going to talk about topic 5, which is capacitance. Okay, the things that we are going to discuss here is going to be what is the function of capacitors and how to get the formula for the capacitance and the relationship with the charge and also potential difference. And definitely we are going to discuss about the arrangement of capacitance. We have two arrangement of capacitor, which is parallel and also series. Okay, and then from there we are going to discuss the potential energy of capacitance, and the last one going to be the capacitor with dielectric. Okay, so let's start. Okay, so basically the function of capacitor is to store the electric charge. Okay, so capacitor is basically consists of two conducting plate. Okay, consists of two conducting plate, and the reason why is a conductor is because this conductor have a free electron, which means that the electron are going to move randomly. So that's the reason why we need to use conductor. Okay, so we have two conductor plate, and in between the conductor plate we are going to have a dielectric material, but that one going to be discussed in the last part of this topic. Okay, but now we are going to discuss with the middle is only vacuum space. Okay, so these two conductor are going to be like close enough. The reason is because we want to increase the capacitance. That one we are going to discuss the relationship between the distance between the two conductor and also the effect on the capacitance. Okay, so other than the functions of capacitor is to store electric charge, another function of the capacitor that you can actually easily see is definitely for backup power supply. Okay, you definitely are going to realize that if you turn off your computer and then you turn on back, your time and your date doesn't affect. The reason is because the one that give the energy, the one they give a power supply to the computer during turn off mode definitely is from capacitor. Okay, and you can actually see that capacitor also can be used in camera flash. Okay, and the other functions also in the keyboard of the computer. When you can actually see that the keyboard is like consists of this two conductor, and what happens is when you press any keyboard, what happening is going to change the value of capacitance, and from there is going to read 1 or 0, which is 1 is turned on, 0 it means turn off. Okay, and that's the function of capacitor. Okay, so before we proceed with the formula for the capacitance, you need to understand that there's a one formula we call the Q equals to CV. Okay, so the things that you need to understand here is capacitance doesn't depends on Q and doesn't depends on V. Okay, but Q and V depends on each other, which means that with a very high potential difference, definitely there will be an increase in the charge that are going to be accumulated at the plate. Okay, but capacitance depends on three things, which is one is going to be the distance between the two plate, between the two conductor, okay, the size and the shape of the conductor, and the last one going to be the dielectric material, which is dielectric material is basically the insulator in between the conductor. Okay, you need to understand that in between the conductor they are going to have insulator. It cannot be any conductor, because the things that you need to understand here is for the capacitor. Okay, when you have two plate like this, there's no charge passing through between the two capacitor. Okay, what happened is going to cause some explosion, so because the leakage of the charge. Okay, so the things that you need to understand that charge cannot pass through the between the two conductor plate, and that's the reason why we need to use insulator at the middle in between the plate. Okay, so basically this is the real diagram of the capacitor between the plates. So what happened is going to be rolled as a cylinder, which you can actually see that the shape of the capacitor is look like a cylinder, because you can actually see that it's like roll these two conductor plate and make as a cylinder. But make sure that in between you are going to have a insulator or dielectric material. Okay, so the symbol for the capacitor is going to be just like two straight parallel lines, okay, over there. So this is to represent the capacitor. Okay, so what happened when you connect the capacitor with the battery or any power supply? Okay, so the first thing first that you need to understand is capacitor initially at neutral state, which means that the amount of charge for this side and this side going to be equal amount of charge. Okay, so that's why it's going to be neutral state, which means that proton and electron have the equal amount of charge. Okay, so what happens when you connect to the power supply? Okay, example, I connect to the, here is positive and here is negative. So power supply is the one that give the energy for the charge to move, and the charge that going to move is definitely electron. Okay, so the electron are going to move in this direction, and what happened is going to be put at this plate. Okay, so the things so basically the same thing happens. So the electron are going to move up until this one side become more negative and this one side become more positive, which means that the charge already have equal amount of positive and equal amount of negative, but one plate more negative, one plate is more positive. So what happened is, how we know whether it's fully charged or not? Okay, so for you to know whether it's fully charged, what happened is the potential difference at capacitor will be equal to the potential difference of the battery. Okay, and that's the reason why the charge going to be stop moving. So at the time we can call it as a fully charged. Okay, you can actually assume that first thing first, this is potential difference. Okay, this is the level of potential difference, which is the battery, and then you have another level which is below than this one. This is battery. Okay, and this is capacitor. Okay, because capacitor at neutral state, that's the reason why I put it lower than the battery. Okay, so what happened is when the charge keep moving, and this is going to be increased. So what happened is the level between the battery, okay, and also capacitor will be equal, and that's the moment where the charge not going to move anymore. So that's the moment when you can call it as a fully charged, which means that the potential difference of the battery, I'm going to denote it as a EMF, okay, will be equal to the potential difference at the capacitor. Okay, so that's how you know whether it's fully charged or not. Okay, so we already discussed how the capacitor is going to be charged. Now we are going to discuss the relationship between capacitors, potential difference, and charge. Okay, the things that you need to understand here is the amount of charge. Okay, like I mentioned before, okay, once you connect to the battery, the electron are going to move. Okay, electron are going to move. Okay, so the amount of charge that accumulated at each plate will be equal to the potential difference of the battery. Higher potential difference of the battery means higher energy. Okay, higher energy, it means that more electron are going to be transferred from one plate to the other plate. Okay, so that's the reason why we are going to relate with Q equals to CV. However, you need to understand here is capacitance doesn't depend on charge, okay, and also doesn't depend on potential difference. Okay, it depends on size and shape of the plate. Okay, so it means that if we have larger area of the conductor plate, it means that more charge is going to be accumulated at the plate. So it means that the increase of capacitance. Okay, and also it depends on the distance between the plate. So the decrease of distance between the plate, increase of capacitance, which I'm going to prove it later. Okay, and the third one going to be the dielectric material in between the conductor plate. Okay, so this dielectric material I mentioned before is a insulator. Okay, Okay, so let's talk about the formula for capacitance. Okay, so what happened is you are going to have like one conductor plate, and this conductor plate, these two conductor plate, the distance between them is less than the dimension and the width of the plate. Okay, the things that you need to understand here is d in between, which is the distance between the two plates, should be less than the dimension and the width of the plate. The reason is because we want to get e that uniform, which means that doesn't have fringing. Okay, so okay, example, this is positive and this is negative, so you have electric field which is always moving from positive plate to negative plate. Okay, okay, so I put it this one as a B and put it as a A. Okay, so please remember that the formula from the topic 4, the relationship between electric field and also potential difference, where we are going to get VB minus VA equals to negative integrations of E dl cos theta. Okay. Okay, so example, if you put the charge here, okay, so what happens is the charge are going to move from A to B based on this one, because the B is going to be the final one and A is going to be the initial one. Okay, so the distance is in that directions. Okay, the test charge, which is always be positive, and then the directions of electric field is basically in the opposite direction. So what happened to the angle? The angle going to be cos 180. Okay, 180 degree. So this one can be cancelled out with this one. Okay, so okay, so what happened next is, okay, please remember back the previous topic, where the charge that, example, if you put at the middle, is going to experience the electric field of E equals to sigma over epsilon naught. Okay, one plate of conductor plate, you are going to get E equals to sigma over 2 epsilon naught. But when you put it charge at the middle, so what happened is, just to recall everything back, so sigma over 2 epsilon naught plus sigma over 2 epsilon naught. And the reason why is because plus, when you actually put it at the middle, this is the test charge. Okay, so the plus is going to be repel and minus going to be attract. Okay, because it's moving in the same direction, and that's the reason why you are going to get plus over there. So you are going to get here is sigma over epsilon naught. Okay, okay, so we have between the plate, the electric field going to be E equals to sigma over epsilon naught. Okay, what does stand by sigma? Sigma is basically surface charge density. Okay, so sigma is equals to Q over area, which is charge over charge per unit area. So you are going to put it here. So you are going to get Q equals to A epsilon naught. Okay, okay, so what happened is we are going to put this formula back into this one. Okay, so we are going to get here is, okay, E, okay, the integration, okay, I put it as a VBA, okay, which is negative already being cancelled out with the cos 180 degrees. So you're going to put here as Q A epsilon naught dl. Okay, you're going to integrate from A to B. Okay, okay, so Q, A, and epsilon naught is basically constant because it doesn't change. Charge stay constant, area of the conductor plate also stay constant, and the permittivity of free space also stay constant. So that's the reason why you can actually put it outside. Okay, so you're going to integrate from A to B dl. So in the integration of delta with the integrate, you are going to get L, which is at the end you are going to get Q dA epsilon naught. Okay, okay, so this is the voltage of the capacitance formula. Okay, so now we are going to find the relationship between the voltage, the potential difference with the charge, and also capacitance. Okay, so like I mentioned before, there's a one formula that relate Q and C, which is Q equals to CV. Okay, so you are going to put this formula into this part. So you are going to get here is your capacitance. Okay, I'm going to put that like this, which means that Q over Q dA epsilon naught. Okay, so Q can be cancelled out. So at the end, you are going to get capacitance equals to A epsilon naught over D, which means that the capacitance is depends on the area of the conducting plate. Larger area, more charge going to be accumulated at the plate, therefore increase of capacitance. and it also depends on the distance between the two plates. So if the distance decrease, your capacitance will be increased. Okay, so basically we are going to use this formula a lot, and we are going to use this formula for the next one. Okay, so this is the very simple questions. Okay, you can actually try your best to answer this question. Basically this one to train you to use the formula. Okay, so what happens for the question A, calculate the capacitance of the parallel plate capacitor whose plates are 20 centimeter with times 3 centimeter. Please take note that, make sure that when you have in this kind of unit, make sure you always change into SI unit, and are separated by 1 millimeter of air gap. Okay, so the question asks you to about capacitance, so you can actually use C equals to A epsilon naught over D. Okay, so the area going to be 0.2 times 0.03. Permittivity going to be 8.85 power of negative 12. Okay, and then divided by the D, which is 1 power of negative 3. Okay, so you are going to get the answer is 53.1 picofarad. Okay, so question B, what is the charge on each plate if 12-volt battery is connected across the two plates? Okay, this one you can actually use formula Q equals to CV. Okay, so C already find it at question A. Okay, picofarad, negative 12. Okay, and the voltage is 12 volt. Definitely you are going to get the answer is 6.37 power of negative 10 coulomb. Okay, so let's move to the next question. What is the electric field between the plates? So you can simply use only this formula, which is V equals to ED. Okay, so this formula can only be used if you confirm that the electric field is uniform. Okay, you cannot use this formula for something that electric field is not uniform. Okay, so you already have your V. Okay, so V is going to be 12 volt divided by the distance between the two gap, which is negative 3. So you are going to get the answer is 1.20 power of 4 volt per meter. Okay, and the last one, okay, estimate the area of the plate needed to achieve a capacitance of 1 farad given the same air gap D. Okay, so I already give you the capacitance, so the question asks you to find the area. So you can actually use the formula from same as A, which is C equals to A epsilon naught over D. Okay, so C is 1, so area you didn't know about that, so 8.85 power of negative 12 divided by the same air gap, which is negative 3. So you are going to get your answer is 11.3 power of 8 meters square. Okay, basically this area is like so large, it's like a one big capacitor. Okay, so let's talk about the arrangement of capacitors. Okay, so when we talk about the arrangement of capacitor, definitely this capacitor is connected to the source of voltage or battery, so we can call that circuit as a closed circuit. Okay, if you didn't connect to this battery, it means that is a we call as an open circuit. Okay, so the arrangement of capacitor can be divided into parallel and series. Okay, so let's talk about parallel first. Okay. So for parallel, okay, the things that you need to understand here is going to be arranged like this. Okay, example, like you have like 3 capacitance, and these all 3 capacitance connected to the same battery. Okay, connected to the same battery. Okay, okay, so I put it as a C1, C2 and C3, and this is going to be the battery, which is denoted by the EMF. Okay, so what happened is when you connect to the battery, the things that you need to understand here is directly connect to the positive, which is going to be positive, 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 and this side going to be directly connected to the negative. You can see that negative, negative, negative. Okay, so this is positive, 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 this is negative, negative, negative. Okay, so as if this one capacitor is basically a battery, because you have positive and negative, which means same as the battery here. Okay, so this one also we can actually put it as a battery, and this one also put it as a battery because it's directly connected to the battery, and that's the reason why for the parallel, the potential difference of the V equivalent will be same as V1, V2, and V3. Okay, and where to get this V equivalent? Definitely from the EMF. Okay, because you can see that it's directly connected, and one side going to be positive, another side going to be negative, as if each capacitance, the potential difference, same as a battery. Okay, so what about the charge? Okay, like I mentioned before, okay, this capacitor is basically, you can see that there's have a junction over there. Okay, I'm drawing this one first. Okay, so you can see that there's like junction here, junction here, junction here, junction here. Okay, you can treat the electron here is like a person. Okay, like a fan. Okay, example, this one is like Michael Jackson, this one is BTS. Okay, and this one is Alif Satar. Okay, just to name a few artists. Okay, so what happens is you can actually put the electron as a fan. Okay, so these electrons are going to move in these directions. Okay, and these electrons have their own interest, whether it's interested with Alisata, interested with BTS, or interested with the Michael Jackson. So this electron, example, this first electron interested with Alisata, so it's going to stay at this place. Okay, maybe second electron attracted to Michael Jackson, so it's going to be attracted to this place. Okay, maybe the third electron are going to be attracted to the Alisata. Okay, so this electron have like options to choose which one which one these electron are going to stay, whether it's at Michael Jackson plate, BTS plate, or Alif Sata plate. Okay, but it also depends on the capacitance. Okay, larger capacitance, definitely there's more charge can be put there, okay, in compare with the small capacitance. Okay, and that's the reason why you can actually see that the amount of charge for each plate going to be different. Okay, so you can actually say that the amount of charge of this capacitance 1, capacitance 2, and capacitance 3 will be different, but you need to understand that the amount of charge of Q1 plus Q2 plus Q3, this total charge will be equal to the Q equivalent, which is the Q equivalent. Equivalent is basically the total charge that move because of this potential difference. Example, if you have like 5 volt and the only charge that can actually move with this energy comes from this potential difference is 20 coulomb. So basically 20 coulomb is going to be divided between C1, C2, and C3, which is also depends on the magnitude of the capacitance. But this C1, C2, and C3 to have going to have a charge, which is this total amount of charge will be equal to the charge that moving because of this energy given by this potential difference. Okay, so what is the formula for capacitance? Okay, so you know that Q equals to CV. So when I put it Q equivalent equals to Q1 plus Q2 plus Q3. Okay, so from Q equals to CV, so you're going to get here is C equivalent, Q equivalent, which is equal to C1 V1 plus C2 V2 plus C3 V3. And like I mentioned before, okay, here the voltage is going to be same for each capacitor because it's directly connected to the battery, because each capacitor is directly connected to the battery. So here, and that's the reason why you are going to get your final formula for capacitance going to be C equivalent C1 plus C2 plus C3. Okay, so you can see that because of these combinations of capacitance is going to increase the area the charge to stay. Okay, so you can actually see that from this picture there's a lot of area for the charge to stay, and that's the reason why this combination we can definitely are going to produce a maximum value of capacitance. Okay, so let's proceed with the series. Okay, so when it comes to series, you are going to arrange it like this. Okay, I put it as C1, C2, and C3, and definitely connected to the battery. Okay, so what happened is you can assume that electron is like a water. Okay, so when electron is moving from this plate, okay, is going to stay at this part. Okay, the things that you need to understand here is the charge going to be same value is because of, okay, example, if I zoom this capacitor, so example, I put it as a positive, sorry, here is going to be electron, sorry, I put it as a negative, negative, positive, negative, positive, negative, positive, negative, positive. Okay, because it's neutral, so basically they are going to have equal amount of proton and electron. Okay, okay, so what happened is when you connect to the battery, okay, when you, okay, example, this one is connected to the battery. Okay, so the electron here are going to move. Okay, move. Okay, and then it's going to be stay at here. So because the increased amount of electron here is going to repel the electron at this side. Okay, because the increased amount of electron at this part going to increase the magnitude of repulsion effect, and what happened is to the electron here at this side, this one electron are going to move to this part. Okay, so what happened here is, okay, like I mentioned before, so you have here is, okay, you have 3 electron negative and 2 positive, and here you are going to have two positive and 2 negative, but the negative here already been transferred to this one because of the repel effect, so here you are going to have 1 negative. And you can see that the amount of charge for this one system will be 2 positive, 2 positive, which is positive, and still 4 negative, which means that equal with the original amount of charge. Okay, so what happened, okay, so if example you put negative here, so basically the same effect, the repulsion effect at this side will be increased, and that's the reason why the electron here are going to be transferred here. So what happened is you still have 4 positive, 4 negative for each capacitance, if example your capacitance have the same value. Okay, so that's the reason why the charge before and after moving will be equal, and that's the reason why the Q equivalent will be the same for capacitance 1, for the capacitance 2, and for the capacitance 3. Okay, 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 so what about potential difference? Okay, for the potential difference, okay, you can see that example this one connected to the battery. Okay, so example this one is positive, I put it here, it's like a one large plate over there positive, and this one negative connected to this part. Okay, so you can see that positive negative here, as if this one at the middle will be the voltage at the middle, the voltage of each capacitance will be equal to the voltage of the battery. Okay, because you can see that this one large plate, so the combination of V1, V2, and V3 will be equal to the EMF of the battery. Okay, okay, so that's the reason why you can actually put here as a V equivalent, which is the potential difference of battery, will be the combination of voltage come from the C1, voltage come from the C2, and voltage come from the C3. Okay, so hopefully you can see this one. It's like one large battery here, which is here, combination here will be total, will be same as the potential difference of the battery. Okay, so what is the formula for capacitance for the series? Okay, so because from this formula, so and then we know that Q equals to CV, so we are going to get here is Q equivalent over C equivalent, which is Q1 over C1 plus Q2 over C2 plus Q3 over C3. And I mentioned before, the charge will be same for each capacitor. Therefore, the formula for the capacitor will be 1 over C equivalent plus 1 over C1 plus 1 over C2 and plus 1 over C3. And that's the reason why this combination, we can call it as a minimum combination of capacitance. Okay, so this combination give you a minimum value in compare with the parallel maximum value. Okay, because you can see that here also the place for the charge to stay is only at this part and this part, because these two parts only connected to the potential difference. Plus you need to understand that there will be no charge moving in between the two conductor plate. Okay, okay, so basically this is the summary of what we have learned before, which is parallel and series. Okay, so when it comes to the questions of parallel and series, the things that you need to understand here is, please find the same physical quantity. Okay, the trick for you to answer the questions when it comes to asking you about what is the charge, or what is the potential difference for each capacitance, so definitely you need to find the same physical quantity. Okay, example, if you have like series, okay, series part, you know that when it comes to series part, the same physical quantity definitely going to be charge. And when it comes to the parallel part, the same physical quantity for this one going to be voltage. And that's the trick. Okay, so you are going to find the same physical quantity for each capacitance first, and from there you are going to find the one that is different, which is for the series, the difference is going to be voltage, and the parallel, the difference is going to be charge. Okay, okay, so let's start with the first question, which is this one question is going to be easy, but it's okay, because you are going to learn how to find the potential difference and charge for each capacitor. Okay, okay, so this question, okay, so the question first, okay, mostly when it comes to this kind of question, please find the C equivalent, which is the total equivalent. Okay, so you can see that the C2 and the C3 is parallel, so the formula going to be C2 plus C3, but here you can actually see that C1, C2, C3 denoted by the C, so you can say that at this part I put it as CA, which is the combination of C2 and C3. Sorry, I put it as C23. It's much easy. Okay, C23, which is C plus C. Okay, because it's parallel, so they are going to get 2C. Okay, and then what happens to the combinations is going to be one capacitant, and this you're going to put as a C23. Okay, that's the trick. Okay, when you combine, it's going to combine as one capacitance. Okay, so this one going to be connected with the C1. Okay, okay, and then you have a potential difference over there. Okay, so C1 and C23 is going to be, yes, very good, it's going to be series, so please take note it's going to be 1 over C equivalent, which is 1 over C23 is 2C plus 1 over C. So you are going to find C equivalent, not 1 over C equivalent. This is the common mistakes. Okay, please make sure that you find only C equivalent, not 1 over C equivalent. Okay, so you are going to get here is 2, 3. So I'm going to get here is 2C over 3. Okay, so once you find the C equivalent, then you are going to find the Q equivalent. Okay, that's the trick. Find the C equivalent first, and then find the total charge, which means that the total charge moving because of this potential difference and because of this capacitance. Okay, because charge is come from the capacitance. Okay, okay. So okay, like example, if the question 2, determine the charge on each capacitor, like I mentioned before, find the Q equivalent first, but here they already give you the value of C and the value of voltage. Okay, so we put C equivalent here with some value, so we are going to get C equivalent will be this will be 2 times 3 micro, which is -6, and then divided by the 3. Okay, then you are going to get here is 2 -6, which is 2 micro farad. Okay, so once you find the C equivalent, the next thing that you need to do is you need to find the Q equivalent. Okay, because the question asks you to find the charge for each capacitor, so definitely after you find the C equivalent, then you find the Q equivalent. Okay, okay, let me transfer here first. Okay, so here, okay, I think you can see that, right? Oh, sorry, this one. Okay. Okay, so okay, so we need to find the Q equivalent first. So we are going to get here is Q equivalent equals to C equivalent times V. So we are going to get here is 2 power of negative 6. Potential difference is 4. So you are going to get 8 microcoulomb. Okay, so basically this 8 microcoulomb is the charge then can actually move because of this potential difference of 4 volt. Okay, so okay, I forget this one. When you actually combine this one, these are going to have like one capacitance only, which is this is going to be 1C123 and directly connected to the potential difference. Okay, so C123 from this one going to have the Q equivalent of 8 microcoulomb. Okay, so okay, the next trick is you are going to reverse the you are going to reverse your step, which like before. So for the for you to find the capacitance, you are going to find the C2 and C3, and for this combination you are going to combine with the C1. Okay, right now you are going to reverse. Okay, so means that if you reverse this thing, you are going to get this kind of diagram. So you're going to get this one, which is this one going to be C23, and you have going to have C1 here. Okay, so you are going to reverse the steps. Okay, like I mentioned before, you need to find the same physical quantity. So C23 and C1 have same Q. So same Q going to be, the Q going to be 8 microcoulomb. Okay, because you find it already here. That's the okay, so that's the basically the trick for you to solve this kind of questions. Okay, so both going to have the same Q, therefore you are going to find the V for this one. So example, if the okay, the question already asked you the voltage also. So for the C1 so for the Q1, for you to find the potential difference, going to be the Q1 C1 V1, which means that the Q1 going to be 8 power of negative 6. The value of C1 is 3 power of negative 6. So for the voltage at C1, you are going to get 2.7 volt. Okay, so for C23, okay, you need to find the voltage at C23 first. Okay, basically there are two methods that you can actually use. Either you already know the potential difference of the battery is 4 volt. Okay, like I mentioned before. Okay, so the potential difference for the series combination going to be the total will be equal to the 4 volts. Therefore, you can actually find the V23, which means that it's going to be 4 minus with 2.7. Okay, so you are going to get here is 1.3 volt. Okay, this is like one method. Another method that you can actually use is you already know the Q here because the series are going to have the same charge. So you can use Q equals to C23 V23. Okay, so you can find the voltage at 23 based on this formula. Okay, so it's up to you. You can use this first method or the second method. Okay, but still you are going to get the same answer. Okay, so once you find already the V23, then reverse the step, which means that you are going to open back the combination of C23. Therefore, you are going to get this shape like this. This is C2 and this is C3. Okay, so example, if C2 and C3 doesn't have the same value, okay, we pretend this one doesn't have any the same value. Okay, so okay, but when you open this thing, you are going to get the parallel combination, which means that the potential difference for this C2 and C3 will be the same value, which is this going to have 1.3 volt. This one also have 1.3 volt. Okay, so what about the charge at C2? So you are going to use the formula, which is Q equals to CV. C is 3 and V is 1.3. So you are going to get here is sorry, it's not 3, right? It's going to be sorry, this is 3 power of negative 6. Okay, so you're going to get 3.9 microcoulomb. Okay, and accidentally the C2 and C3 have the same value, and that's the reason why Q2 equals to Q3. Okay, but example, if Q3 and Q2 doesn't have the same value, how to do that? Okay, so you just use also this formula for you to find the Q at 3. Okay, so the things that you need to remember, that find the C equivalent first, and from the C equivalent you find the Q equivalent, and the trick for you to answer this kind of question, for you to find find the charge and voltage for each capacitor, is you need to find the same physical quantity, whether it's going to be Q or it's going to be V. Okay, let's move on to the next question. Okay, so this question is quite different from the previous one. Okay, so the question asks you to find the charge of each capacitor and the voltage across each capacitor, and they didn't give you any voltage when it's connected to VA and VB, but they already give you the charge at Q3. Okay, so Q3 have 23 microcoulomb. Okay, and the things that you need to understand, that C3 and C4 parallel, which means that the charge is going to be different. Okay, so how to solve this kind of questions? Okay, because it's parallel, so definitely the one that going to have the same physical quantity is going to be a voltage. Okay, so we find the voltage here first, because we already know the charge and we already know the value of C3. So V3 equals to which is going to be Q3 over C3. Okay, so Q3 you get 23 microcoulomb and C3 is 8 microcoulomb. Okay, so you are going to get your potential difference here will be 2.9 volt. Okay, because C3 and C4 is parallel, so it means that this one going to have 2.9 volt and this one also have 2.9 volt. And accidentally the questions for C1 and C2, C1 is basically the same value of C3 and C2 have the same value of C4. So you can actually put here as V1 equals to V2 equals to V3 equals to V4, which is going to be 2.9 volt. Why the voltage going to be the same is because it's parallel. Okay, and accidentally the C1 and C3 have the same value and C2 and C4 have the same value. Okay, so so I can actually put here is, so C1, C1 also have the C1 same value with the C3, therefore the charge for C1 going to be 23 microcoulomb. Okay, and the voltage is 2.9 volt. Okay, so for the C4, we find the potential difference for this. We find the charge for C4. We already know voltage and capacitance. So Q4 going to be, C4 is 16 micro times with the voltage, which is 2.9. So you are going to get for your Q4 is going to be it's going to be 46 microfarad, right? Of 0.64 power of -5 coulomb. Okay, so because C2 and C4 have the same capacitance, therefore we can actually put that Q4 equals with the Q2, which is 4.64 power of -5 coulomb. Okay, so we already find the charge and voltage for each capacitance. Therefore we need to find for the question C the voltage VBA across the com. Okay, so this one C1 also have 2.9 volt, which means this combination going to have a 2.9 volt. Okay, I'm going to put it here. So the combination of C1 C2, so C1212 going to have a potential difference of 2.9. Okay, and the C23 also have the same potential, which is 2.9. Okay, so for you to find the potential difference from A to B, you just add up the potential difference from here and here, because it's series, right? So it means that this combination are going to produce voltage of the battery, which is 2.9 plus 2.9. Therefore the voltage of the battery you are going to get is 5.8 volt. Okay, so that's how you do it. Okay, so whatever things happen, just find the same physical quantity between the capacitance, and from there you can actually find the charge or potential difference for each capacitor. Okay, so other than the arrangement of capacitor, there's basically another type of questions where capacitors reconnected. Okay, so for you to solve this kind of questions, basically it's the same thing. We are going to relate with the conservation of charge. Okay, so I'm going to explain for this one, and you can use this working solve for any questions that same as this one. Okay, So what happened is when you connected the capacitance with the battery, okay, so definitely there will be a charge moving between the battery, charge moving because of this battery, okay. So you have C1 here, C2 here, and then you have 24 volt here, okay. So we assume that it's fully charged, therefore we need to find the charge accumulated at C1 and what is the charge at C2, okay. So you're going to Q equals to CV, okay. So you are going to here is 2.2 power of -6 and the voltage is 24. So you are going to get here is 5.28 power of -5 coulomb. Okay, the same thing that you're going to do for the C2. Find the charge first, which is C2 is 1.2 power of -6 and the voltage is going to be 24. Therefore, you're going to get here is 2.88 power of -5 coulomb. Okay, so the things that you need to understand that once you disconnect it from the battery, okay, once you disconnect it from the battery, charge are not going to move, okay, because you need to understand that charge are going to move because of the energy given by the battery. But once you cut it from the battery, definitely there will be no energy for the charge to move, okay, there will be no energy for the charge to move, okay. So it means that this C1 and C2 are going to have charge 5.28 and 2.88 -5 coulomb. Okay, so okay, next is okay, the capacitance, the combination of this capacitance is disconnected from the battery, okay. So but then it's going to be reconnected with a different leg, with a different sign, okay. So what happened is, okay, example, this is positive, positive, negative, negative. So it's going to reconnect it like this, negative, okay, so this, okay, like this, which means that they are going to connect it with this is plus, this is minus, and this is minus, then this is plus, okay. This is Q1, sorry, this is Q1, this is Q2 and Q2, okay. The things that you need to understand that even though this capacitor already disconnected from the battery, is going to move because of this different in terms of sign, okay. You can actually say that when you have full charge battery, so basically what happens is this plus and this plus is like the same level, which means that the charge are not going to move. But once you have difference level, example, you have this is plus and this is negative, charge are going to move because of difference in terms of potential difference, okay. Okay, that's the reason why the charge are going to move because of this positive and negative up until they are going to reach equilibrium. Okay, what does it mean by equilibrium? Equilibrium, it means that both charge, both plate, this upper plate, are going to have the same charge, the same sign of charge, whether it's positive, positive, or negative, negative. Then at that time, equilibrium, it means that no more charge are going to move, okay. Okay, so basically how this moving of charge are going to make the sign of the plate positive, positive, or negative, negative. Okay, I'm going to explain it here first, okay. That the diagram that I already draw it for you, okay, maybe I'm going to put it here, sorry, okay, the bottom here, okay, okay. Okay, so the amount of charge, it depends on the magnitude of capacitance, okay. So the things that you need to understand that even though this plate is positive plate, doesn't mean that all the charge there is going to be positive. There will be a negative, but the majority of the charge is positive, and that's the reason why we put it, we denoted it as a positive plate, okay. So what happened is the electron here are going to move because of attract to the positive charge. So once you have negative here, because still majority of the positive here, that makes this plate positive, and this one already transfer, and this one going to be positive, and that's the reason why you are going to have positive plate and positive plate at this side, okay. And this means that this one equilibrium already reached. Okay. Okay, so same as goes as this one, okay. The electron here are going to be attracted to this one, so what happens, they are going to be majority negative here, and that's the reason why this is going to be negative and this plate going to be negative, and it means that equilibrium has reached, okay. So it means that there will be no more charge once you reach equilibrium, okay. Okay, so The question asks you to find the charge on each capacitor and the potential across each after equilibrium is established. Okay, you need to understand that if you reconnect it with the opposite sign, the charge are going to move, but the total amount of charge still equal to the total amount charge of this one. Okay, because this is only the charge that can move when it's connected to the battery, but once it's reconnected with different sign, there's some of the charge are going to move, like I mentioned before, electron moving here. So we need to find the new charge for the new charge for each capacitance once it reach equilibrium. Okay, so for you to solve these questions, you are going to look at this part. When it's reconnected, you are going to use the formula of conservation of charge. Okay, conservation of charge. Okay, conservation of charge, it means that the charge cannot be created, cannot be destroyed, okay, but can be transferred between the capacitance. Okay, so once you reconnected like this, okay, the original charge going to be 5.28 and 2.88. You need to find the net charge before and the net charge after it reach equilibrium. Okay, so I'm going to put it as a Q1 minus Q2. Why is become minus? Because you reconnected plus with the minus. Okay, you can choose plate, the upper plate as your equations, but you can actually use the lower plate for your equation. It's up to you, but make sure that if you choose the upper plate, after equilibrium you also choose the upper plate. If you choose the lower plate, after equilibrium you are going to choose the lower plate. Okay, so the Q1 minus Q2 will be equivalent to after the equilibrium has reached, which is going to be Q1 plus Q2. Okay, I'm going to put the capital Q as a before equilibrium and the small q as a after equilibrium. Okay, so we are going to find the net charge first, which is 5.28 power of negative 5 minus 2.88 power of negative 5. It's going to be Q1 plus Q2 because we didn't know what is the charge at Q1 and Q2 yet. So Q1, Q2, the net charge for this one going to be 2.4 power of negative 5 coulomb, which that this 2.4 negative 5 coulomb is the only total charge that can actually move when you reconnect it with the opposite sign. It cannot be more than 2.4, it cannot be less than 2.4. It's going to be exactly net charge equals to 2.4 negative 5 coulomb. Okay, so we find first the potential difference. Okay, the things that you need to understand here is going to be reconnected parallel. Okay, so it means that when it's reconnected parallel, it means that the potential difference for both are going to have the same value. So I'm going to use the formula of Q equals to CV. Okay, Q equals to CV. This Q is basically the combination of this, which means that the net charge going to be 2.4 negative 5 coulomb. 2.4 negative 5 coulomb. Okay, so C is the combination of both capacitance because it's parallel, so you just add up. So we are going to get 2.2 power of negative 6 plus with 1.2 power of negative 6. Okay, and V. Okay, so here you are going to get your potential difference for each capacitance after reconnected and after equilibrium established. You are going to get 7.06 volt. Okay, so you can actually see that the potential difference is already changed. Okay, if example this capacitor is still reconnected to the battery, definitely potential difference is going to be 24 volt. Okay, but once you disconnect it from the battery, it's going to have different value. Okay, so after you find the potential difference, definitely you are going to find the Q1 and Q2 here. Okay, so you just use Q1 equal to CV. Okay, we are going to find charge for each capacitor. So we're going to be 2.2 negative 6 times 7.06. So for the Q1, the charge that are going to stay there are going to be 1.55 negative 5 coulomb. Okay, and what about Q2? Okay, so you can just use Q equal to CV, or you can just use 2.4 because this is total charge, which means that 2.4 power of negative 5 minus with 1.55 power of negative 5. So you are going to get here is 8.8 8.47 power of negative 6 coulomb. Okay, so you can actually use this one because you already know the total charge, so you just minus with that, or you can actually use formula of Q equal to CV for C2. Okay, so let's proceed to the next one. Okay, so basically this kind of question looks almost the same with the previous one, but this one you only have one capacitor that fully charged and is going to be reconnected with the capacitor that uncharged. Okay, so we are going to use the same kind of method. First thing first, we are going to find charge at capacitor 20 microfarad. Okay, so going to be Q equals to 20 negative 6. So you are going to get here is 1.20 power of negative 4 coulomb. Okay, so basically what happened is when it's fully charged, this capacitor of 20 microfarad are going to have a charge of 1.20 negative 4 coulomb. Okay, after that it's disconnected from the battery. Okay, you need to remember that once it's disconnected from the battery, this charge are going to be permanently there. Okay, it's not going to move. There's no more energy for the charge to move. Therefore, this is the amount of charge that going to be stay at that 20 microfarad plate. Okay, so we need to find the potential difference across the capacitance. Okay, but now this 20 microfarad is reconnected with the uncharged capacitor. Okay, so basically neutral. So what happened is, okay, because like I mentioned before, if you have like difference in terms of level, this is like 20 microfarad, which is already fully charged, and this one is the uncharged capacitor of 5 microfarad. The electron are going to move up until both charge in the same level, which means that both charge have the same positive and negative. At that time, it means that equilibrium has reached. Okay, there's no more charge moving. Okay, so we are going to use the same kind of method, which means that we are going to use conservation of charge. So I'm going to put as Q1 plus Q2. This one going to be the initial, okay, equals to Q1 plus Q2. This one going to be the final. Okay, it means that the initial is when you reconnected with the uncharged capacitance. Okay, so Q2 is basically 0 because it's neutral. So here the amount of charge before going to be 1.20 power of negative 4 coulomb. Okay, so it's going to be equals with the net charge after equilibrium has reached. Okay, so use the formula of Q equals to CV. So you are going to get here is Q1 plus Q2. This is basically Q. Okay, C is the combination of capacitance, which is 20 plus with the 5, you are going to get 25 microfarad. Okay, and you need to find the V. Okay, the V here going to be the same for 20 and 5 because it's parallel. Okay, so you are going to get your V is 4.80 volt. Okay, so okay, but you need to understand here why it's going to be positive here is because it's uncharged. That's why it's going to be 0. By example, if like previous one you reconnected with the opposite sign, which is this one going to be positive, this one going to be negative, therefore you need to put negative here. Okay, but this one, once equilibrium has reached, definitely you are going to have the same sign of plate, okay, for the upper part and for the lower part. Okay, so once you already get the voltage, definitely you are going to get for the charge. Okay, so you just use U equals to CV. Okay, so you need to find the Q at 20 microfarad. So I'm going to use 20 negative 6 with the voltage of 4.8. So you are going to get here is 9.60 power of negative 5 coulomb. And for Q, 5 microfarad. This is one example. This is 5 microfarad. Okay, you are going to get is 2.40 power of negative 5 coulomb. Okay, so basically is logic because Q1 have a higher magnitude of capacitance, therefore they're going to have more charge at 20 microfarad in compared with 5 microfarad. Okay, so hopefully you understand how to do this kind of questions. Okay, hopefully basically the working set is almost the same, but the things that you need to be extra careful is for the initial part where there is going to be connected in series or parallel. Okay, but the things that you need to understand is you need to find the total charge, which is the net charge before, and use the conservation of charge, and then you make it this equation, which is charge before, net charge before equals to net charge after, and from there you find the potential difference, and after that you find the charge for each capacitance after equilibrium has reached. Okay, okay, let's move on to the next part. Okay, so like I mentioned before, once you connect it to the battery, the charge from plate going to have some energy to move from one plate and then put it to another plate. But the things that you need to understand here is the capacitors not going to be charged instantaneously. Okay, not going to be that quick. Okay, the reason is because of, okay, example, I put this negative, positive, negative, positive, negative, positive, negative, positive. Okay, okay. So initially, the capacitor is going to be a neutral state. So once you connect it to the battery, the electron are going to move because already received some energy. So if electron put at this place is not going to have any work done because there's no repulsion effect, because this plate originally at neutral state. Okay, so but once the second electron moving and then put it at this plate, is going to feel some repulsion effect comes from the previous electron, and a previous electron that stay there. Okay, and that's the time that you need to have a work done for you to put this electron at this plate. Okay, and that's the reason why the capacitor not going to be charged instantaneously. Okay, it's because of repulsion effect come from the electron. Okay, okay, so when you put the first charge, okay, so you don't have any work done, but when you put the second, third, and fourth, and so on, okay, you need to have a work done. So we need to find the work done to put the one small charge first. Okay, so definitely we need to have, okay, we know that V equals to U over Q. Okay, so basically we need to find one energy for one small charge to move. Therefore we are going to have du delta U equals to V delta Q. Okay, the potential difference is not going to have any changes because it's connected to the battery, but this one is basically the energy to move one small charge. Okay, but if we want to find like the whole amount of charge that already moved because of this potential difference, and we need to find the potential energy, definitely we are going to integrate. Okay, integrate from what? From 0 to until full charge. Okay, so the integration of delta, definitely you are going to get U here. Then you need to put V here based on formula Q equal to CV. Therefore you only have Q over C. So I'm going to put it here as 0 to Q, which means that Q over C dQ. Capacitance will be constant. Therefore we're going to put it outside. Okay, this one going to be Q dQ. So the integration of Q dQ, you are going to get 1 over C, which is 1 over 2 Q square. Okay, that's the Q and TQ, and that's the reason why you are going to get your final formula is U, which is the potential energy, will be equals to 1 over 2 Q square over C. Okay, so basically this is the energy for you to move the whole amount of charge from one plate to another plate. Okay, this is the total potential energy. Okay, so you can actually use this formula 1 over 2 Q square over C, or you can actually use another formula, but you need to refer to Q equal to CV. Okay, I put the Q here to this part, so I'm going to get 1 over 2 C square V square over C. Therefore you can actually use this equation for you to find the potential energy, which is 1 over 2 CV square, or another formula going to be you put C as your C as your subject, you put it here, so you're going to get U equals to 1 over 2 Q square Q over V, which means that is going to be U equals to 1 over 2 QV. Okay, so you have three formula for you to find the potential energy. Okay, basically, but this one is going to be the original one derived from this formula. Okay, okay, but the things that you need to understand that capacitors are not going to be charged instantaneously, okay, because of the repulsion effect. Okay, so this is basically the formula they already derived for you. Okay, okay, so basically you can assume that for the capacitor to charge, it seems like this charge is moving with some ladder, because you have like potential difference of positive and negative. But the things that you need to understand here, the positive charge not going to move, the one they're going to move is negative. Okay, so this is going to have some corrections over there. Okay. Okay, alright, so this one, the question is like pretty easy. It's very direct question. You just use the formula for you to find the electric energy, which means that this one already give you 150 microfarad. Okay, and they already give you the the voltage, so you can actually use formula of U equals to 1/2 CV square. So definitely you are going to get the answer is 3 joule. And the same goes with the question 2. What is the power output? Okay, the things that you need to understand, the relationship between power and energy is going to be, power is basically change of energy, the rate of change of energy. Okay, du over dt, delta u over delta t. The things that you need to understand is power is basically how much energy has been transformed to another types of energy. So example like 50 joule already been transformed from potential to heat. Okay, so that is going to have some power. Okay, so power is basically how much energy has been transformed to the other types of energy. Okay, so you can use this formula for you to find the power. They already give you 1/1000 seconds. Okay, so P equals to U over T. So U you already get from the first one. Okay, and then time is 1/1000. Therefore, you're going to get your power is 3000 watt. Okay, that is basically direct questions. Okay. Yeah. Okay, so for this question also is quite direct questions. Okay, the question asks you to find the energy stored for each capacitor. They already give you the capacitance and they already give you the coulomb. So definitely you can use the formula of U equals to 1/2 Q square over C. Okay, because I already give you the charge and also the capacitance. Okay, then you're definitely going to get the answer. Okay. Okay, so this is basically the concept test. Okay, so the question asks you, how has the energy stored in this capacitor changed if, example, you have two parallel plate that is basically connected to the battery and then disconnected, and then these two plates are initially separated by a distance d. Okay, so when the things that you need to understand that once it's disconnected from the battery, the charge are not going to move anymore. So means that if example you charge to 50 coulomb, so once you disconnected from the battery, your charge also have 50 coulomb. Okay, because there's no more charge moving. Okay, so the charge is going to be constant. Okay, Q is going to be constant. Okay, and then the two plates are initially separated by the distance d. Okay, what are the effect of d to capacitance? Okay, what the effect of increase d to the capacitance? C going to be decrease based on formula C equals to A epsilon naught over D, because you pull this thing apart, so definitely C going to be decrease. Okay, so we need to find the energy. Okay, so I'm going to use formula of U equals to 1/2 Q square over C. Okay, because capacitance is already decreased by 2 because you separate into 2D, and your Q is constant, so what happens to your energy? Yes, it's going to be increased by double. Okay, so that's how you do it. Okay, so but the things that you need to understand that because one plate is positive, one plate is negative, for you to pull these two plates apart, definitely you need to have some energy, because positive and negative going to be attracted to each other. So if you want to pull these two plates apart, definitely you need to have work done, which means that you are going to have increase of potential energy. Okay. Okay, when we talk about the energy, definitely we need to talk about the energy density. Okay, the things that you need to understand here is, if I've said potential energy is basically the energy that going to be stored in a capacitor, which is basically stored in the electric field. Okay, I repeat, the potential energy is basically the energy stored in the capacitor, which means that it's going to be stored inside the electric field, which is going to be in between the plate. So we need to find the energy density for energy stored inside the electric field. Okay, so we derive the equations of U equals to 1 over 2 CV square. Okay, please remember that C, when relate with the area and area and D, is going to be C equals to A epsilon naught over T, and V you are going to put E D. Okay, so you are going to get here is U 1 over 2 A epsilon naught D E square D square. Okay, so when we talk about to find the energy density, so definitely we need to divide it by volume or area or length, but this one you are going to divide by the volume, which is the volume going to be the volume between the plate where the electric field exists. Okay, so what happened is when we divide both sides by volume and this side also by volume, so we are going to get here is, I'm going to this out this one. Okay, area with D, because area times D, definitely you are going to get volume here. So U over V, you are going to get energy density, which are going to be denoted by the small u. Okay, so here you are going to left with 1 over 2 epsilon naught E square. Okay, so we can actually say that the energy density is going to be proportional to the square of the electric field. Okay, and the unit for it going to be joule per meter cube. Okay, so this is how you find the energy density. Okay. Okay, so we are going to discuss the last part in chapter 5, which is capacitor with dielectric. Okay, and what does it mean by dielectric? Dielectric is basically an insulating material which we are going to place that dielectric in between the conducting plate. And the reason why we need to use the dielectric material is because it's going to increase the capacitance. Okay, like I mentioned before, before this we discussed about two conducting plate, but there's air in between, and the reason why we need to use dielectric is because it's not easily break down in compare with air. Okay, what does it mean by breakdown? Okay, breakdown, it means that when you expose insulator or air very high electric field, what happen is this dielectric material are going to become a conductor, and when you put the conductor in between, what happen? Definitely there will be a charge moving from one plate to another plate, and definitely this capacitor can easily explode or is failure to become a capacitor. Okay, and that's the reason why we need to make sure that we put an insulator in compare a conductor. And basically air easily to break down, and you can actually see from the from this table, air, the dielectric strength is only 3 power of 6 in compare with other types of dielectric material, and that's the reason why we need to put insulator other than air to make sure that this capacitor can be functioned as a capacitor where there's no charge movement between the conducting plate. Okay, so another thing is the reason why we need to put the insulator is because based on equation C equals to A epsilon naught over D, okay, the capacitance will be increased with the decrease of D, which means that the distance between the two conducting plate definitely will be decreased if you put a very thin layer of insulator. Okay, so that's the main reason why we need to use dielectric material in compare air. Okay, so next we are going to discuss the effect of dielectric material to voltage, charge, and electric field, where we are going to have two rules. First one going to be where charge going to be constant, and another one going to be where potential difference going to be constant. Okay, like I mentioned before, the capacitance will be increased when you put a dielectric material between the two conducting plates, because the distance between the two conducting plates already decreased. But what factor is going to be increased? Okay, so the new value of capacitance will be increased with the value of K. Okay, K is basically constant value. Okay, and this constant value depends on the dielectric material. So each dielectric material have their own constant value. Okay, and the C naught here is going to be the capacitance, where the space between the two conducting plate is a vacuum, or you can actually say that the capacitance without dielectric material, and this new value of C is going to be when you actually put the dielectric material in between the two conducting plate, or you can actually say that with the dielectric material. Okay, so we need to find the relationship between C and A and D. Okay, like I mentioned before, the original capacitance, where the vacuum is going to be in between the conducting plate, is going to be A epsilon naught over D. But for you to get the new value of C, where you already put the electric material, is going to be A K epsilon naught over D. Therefore, we can actually say that if you need to find the new permittivity, this permittivity is going to be the permittivity when you put the dielectric material is going to be K multiplied with the epsilon naught, which is this epsilon naught is the permittivity of free space, and the value is 8.85 power of negative 12. Okay, so make sure that when you need to use the permittivity, make sure that you multiply with the value, with the constant value of dielectric material, for you to find the new permittivity with dielectric material. Okay, so we already talked about capacitance and the permittivity. Let's talk about the effect of dielectric material to energy density. Okay, without dielectric material, your energy density going to be 1 over 2 epsilon naught E square. But when you put the dielectric material, so it means that it's going to be 1 over 2 K epsilon naught E square. Okay, therefore we can actually put it this one as a 1 over 2 epsilon E square. So this is going to be the value of permittivity with dielectric material. Okay, so next we are going to talk the effect of electric field, charge, and potential difference when you are going to have a constant value, whether it's going to be charge or potential difference. Okay, this one I already derived it for you. Okay, so the first part that we are going to discuss is where we want to make sure that our voltage is constant. Okay, so what happened is, when you put the dielectric material in between the two conducting plate, you are still connected to the potential difference. Okay, so before you put the dielectric material in between the two conducting plates, the arrangement of the charge inside the insulator is going to be like this. It's going to be randomly positioned. Okay, but once you put it inside the region of electric field, which is between the two conducting plate, what happened is the charge to be polarized, where the negative here are going to attract to the positive plate, and the positive over there are going to facing with the negative plate. Okay, so what happened is, in between this molecule, they are going to produce an electric field where it's moving from positive to negative, where it's going to be in that direction. Okay, and definitely for the two conducting plate is going to produce the external electric field, which basically to the right. Okay, so what happened is the net electric field going to be reduced. Okay, the reason is because electric field inside the insulator, which is moving to the left, will be cancelled with the external electric field, which is moving to the right, and that's the reason why inside the insulator the electric field going to be 0, and that's the reason why the net electric field will be reduced. Okay, so what happened to V? Okay, based on formula, V equals to ED. D is going to be the distance between the two conducting plate. Definitely is going to be constant. So when E is reduced, definitely your potential will be reduced. However, you want to make sure that your voltage is still constant. Okay, so how to do that? Okay, so when you're still connected to the battery, so the battery will still gives the energy to the charge to move from one plate to another plate. Therefore, there's an increase of charge at each plate to make sure that the potential difference of the battery, the potential difference of the capacitor will be equal to the potential difference of the battery. Okay, so the capacitors there going to be increased with the factor of K. So the Q naught here is the original capacitor, where you don't have any dielectric material in between the plate, and the Q here is going to be the new value of Q. And the reason why is going to be increased is to make sure that our voltage to be constant. Okay, this is basically a proper diagram that you can actually see that when you put the insulator in between the two conducting plate. So what happened is the negative over there are going to be attracted to the positive plate, and the positive there are going to be attracted to the negative plate. Okay, it's still moving, but moving within the molecule. Okay, so what happened is the net E going to be reduced because of the electric field inside the insulator, we call the E induced, will be cancelled out with the external electric field from the plate. Okay, so this is also one of the diagram. You can actually see that where the charge going to be polarized and the effect of this to the V and E. Okay, let's talk about charge constant. Okay, now this is the second situation where we want to make sure that our charge is constant. Okay, the things that you need to understand that if you want to make your charge constant, definitely you need to disconnect that circuit from the battery. Okay, so what happened is, first thing first, you are going to charge your capacitor. Okay, and then you disconnect it from the battery. Once you disconnect it, then you put the dielectric material. Okay, the reason is the same like the previous one that I mentioned to you. Okay, where your E going to be reduced is because the electric field induced, which is electric field inside the insulator, will be cancelled out the external electric field. So your E going to be reduced with what factor? So your new value of E going to be reduced with the value of K. So your E naught divided by K. So this E naught is going to be the original electric field without dielectric material. So this is going to be with dielectric material. So when E is reduced with the factor of K, definitely your V also reduced with the factor of K. But please make sure that this one disconnected from the battery. If you still connected to the battery, definitely your V going to be constant. Okay, which means that at a particular point your charge will be increased. But this one, we want to make sure our charge is constant. Okay, so if we want to make sure our charge is constant, definitely we need to disconnect that from the battery, because you need to understand that when you connect it to the battery going to give the energy to the charge to move from one plate to another plate. But once you disconnect it from the battery, there will be no more energy come from the battery. That's the reason why your charge going to be constant. Okay, so your E reduce, your V also reduce. Okay, but for both situation, voltage constant and charge constant, your C definitely will be increased with the factor of K, because the distance between the two conducting plate already reduced. Okay, so let's test our concept with this question. Okay, so this one, the capacitor is still connected to the power supply when dielectric material is inserted between the plate. So after the dielectric is inserted, does each of the following quantities increase, decrease, or remain the same? Okay, when you put the dielectric material, definitely your capacitance will be increased, because your D, the distance between the two conducting plate, decrease. And when you connect to the power supply, okay, definitely your voltage will be constant. Okay, at the first place, your voltage will be reduced because your E will be reduced. And that's the reason why when you connect to the potential difference of the battery will give the energy to the charge to keep moving from one plate to another plate up until the voltage of the capacitor will be equal to the voltage of the battery. And that's the reason why this one does going to be remain the same, and the charge stored on the plate definitely increase to make sure that the voltage of the capacitor equal to the EMF of the battery, and the electric field also remain the same. Okay, so this is one of the another conceptual questions. Okay, so but this one, okay, you charge a parallel plate to the capacitor, but then you disconnect it from the battery, and then what happened is you pull the plates apart to the largest separation. Okay, so do the following quantities increase, decrease, or stay the same? Okay, so the things that you need to understand here is when you disconnect it from the battery, definitely there's no place for the charge to move. There's no energy to give the charge to move. So definitely your Q will remain constant. Okay, remain constant. So here your Q definitely stay the same. Okay, but what happened to the capacitance? Okay, when you pull the plates apart, definitely you are going to increase your D. So based on formula of C equals to A epsilon naught over D, Okay, so when you increase D, definitely your capacitance will be decreased. Okay, very good. Okay, so what happened with the electric field between the plate? Okay, so based on the formula of E equal to sigma over 2 epsilon naught, this is the formula for electric field for one plate. So your your sigma here is charge per unit area. So when your Q is remain constant, A also remain constant. That's the reason why your E also stay the same. Okay, so this one going to be stay the same. Okay, so what about the potential difference? Okay, the potential difference will be increase or decrease. Okay, so we are going to look at Q equals to CV. Okay, V equals to Q over C. So Q going to be remain constant. C definitely will be decreased. Therefore, your V will be increased, inversely proportional. Okay, so this one going to be increased. Okay, so what about the energy store, the potential energy store in the capacitor? So you can actually use the formula, which is U equals to 1 over 2 Q square over C. So when your C is decreased, definitely your potential will be increased. Okay, the additional energy is basically come from the work that you do in pulling the two plates apart, and that's the reason why your energy store definitely will be increased. Okay, let's move on to the next question. Okay, this question is looks like the same as the previous one, but this one the battery still remain connected to the capacitor, and why you pull the plates apart. Okay, the things that you need to understand here, when your battery remain connected to the capacitor, definitely your V will be constant. Okay, so definitely constant or stay the same. Okay, so what happens to the C? Okay, same like previous one, when you use the formula of C equals to A epsilon naught over D, increase of distance between the two plates, definitely your capacitance will be decreased. Okay, so what happened to the charge? Okay, so based on the formula of Q equals to CV, okay, remain the same and your C decrease, therefore your Q also decrease. Okay, next, electric field between the plates. Okay, so we are going to use the same formula like previous one, which is E equals to epsilon naught, sigma over 2 epsilon naught. Okay, so sigma is basically charge per unit area. Your charge at the plate already decreased. That's the reason why your electric field also decrease. Okay, yeah. So V is constant because the presence of the battery. And what happened to the energy store in the capacitor? Okay, so you can actually use the formula of U equals to 1 over 2 CV square. Okay, so your V is constant, your C is decreased, therefore your energy definitely will be decreased. Okay, because you need to understand here is the electric field or electrostatic force between the two plates is already decreased. Therefore, you didn't need that huge energy for you to pull the plates apart because the electric field or the electrostatic force or the attraction force between the two plates already reduced. Okay, let's move on to the next question. Okay, this question is almost look like the first one that we discussed. Okay, this one, they're still connected to the battery. Yes, battery, and then disconnected, and the plates are then pulled apart with a factor of 4. Okay, so for this one, if the question asks you by what factor, you need to answer it increase by double, increase by triple, increase by 4 or something like that. Okay, so like I mentioned before, when you disconnect it from the battery, definitely your charge will be constant. Okay, so did the potential difference decrease by the factor of 4? Yes, your potential difference will be increased. Okay, with the formula of Q equals to CV. Okay, C decrease, V you need to find the V. So Q is remain constant. That's the reason why you get your V increase. Okay, by what factor did the electric field change due to this increase in distance? Okay, same thing. You use E equals to sigma over 2 epsilon naught. This is charge per unit area. Your charge remain constant. Definitely your electric field will be constant, no change. Okay, by what factor did energy stored in the electric field change? Okay, make sure that you indicate whether the energy increase or decrease. Okay, it's going to increase by the factor of 4 because we are going to use the formula of U equal to 1 over 2 Q square over C. So your C decreased by the factor of 4, so your potential energy definitely going to be increased by the factor of 4. Okay, so D is you insert the dielectric material to completely fill the volume between the plate. So what happens to your energy store? Okay, so when you put the dielectric material inside the plate, your capacitance will be increased. Okay, but now you need to understand that you put the dielectric once you disconnect it from the battery. Okay, so we are going to use the formula of, okay, so you are going to use U equals to 1 over 2 Q square over C. Okay, so when you put the dielectric material, your C definitely will be increased because distance between the two conducting plate already decreased, and your charge remain constant because it's disconnected from the battery. So definitely your U will be decreased. Your potential energy already decreased. Okay, and the reason is because of when you put the dielectric material, your E will be reduced. Okay, so once your E reduced, definitely your electrostatic force to reduce. Okay, so when your electrostatic force is the one that basically the attraction force between the plate reduce, and that's the reason why you didn't need that higher energy to pull the plates apart. Okay, because the electrostatic force or the attraction force between the plate already reduced. Okay, so okay, this one is basically the calculation questions. Okay, so we are going to answer the first one. Okay, but we need, you definitely, first thing first, you need to understand the situation. This one, the capacitor is already filled with the dielectric material with a factor of 3.4 and is connected to the 100-volt battery. Okay, after the capacitor is fully charged, the battery is disconnected. Okay, the plates have area A and are separated by D. Okay, find the capacitance, the charge, the electric field, and the energy store. Okay, so for the capacitance, okay, so you are going to use C equals to A epsilon over D. Okay, so the epsilon here, where to find it? Use epsilon equals to K epsilon naught. Okay, so you need to find the permittivity of dielectric material. So it's going to be here is 3.4 times 8.85 power of negative 12. Okay, negative 12. Okay, so you are going to get here is, so you are going to get 3 power of negative 11 Coulomb square over Newton meter square. Okay, so you are going to put it inside this formula. Okay, so so C equals to area is 4 times 3 power of negative 11 divided by the power of negative 3. Make sure that you change into SI unit. Okay, so you are going to get 3.0 power of negative 8 farad. Okay, so the question asks you to find the charge on the capacitor, so you can actually use Q equals to CV. So Q equals to 3 negative 8 times V is 100. Okay, so you are going to get here is 3 power of negative 6 coulomb. Okay, the electric field strength. Okay, for the electric field strength, you can actually use the formula of V equals to ED. Okay, so V is 100. Okay, E and D is 4 negative 3. Okay, so you are going to get your electric field is 25 power of 3 volt per meter. Okay, and how about the energy stored in the capacitors? Okay, I'm going to use the formula of U equals to 1 over 2 CV square. Okay, 1 over 2 C, I'm going to get from first one, which is 3 power of negative 8. And the V is going to be 100. Therefore, you are going to get your answer is 1.5 power of negative 4 joule. Okay, so that is question 4A. Okay, next question B. Okay, I'm going to reduce this. I'm going to put this here. Sorry. Okay, put it here. Okay, so question B. Now your dielectric is carefully removed. So the question asks you to find the new value for capacitance, charge, electric field, and also energy store. Okay, so for this one, okay, when the dielectric material is removed, definitely your capacitance will be reduced. Okay, so you can actually use the formula of C equals to KC naught. So you need to find the C naught, which is without dielectric material. So C naught equals to C over K. So the C here I'm going to get from this one. Okay, So here I'm going to get 3 power of negative 8 over 3.4. Therefore, I'm going to get my answer is 8.8 power of negative 9 farad. Okay. Okay, you need to find the electric field strength. Oh, you don't have to find the charge. Okay, yes, you need to find only electric field strength. So for the electric field strength, okay, when you remove the dielectric material, your electric field the electric field going to be increase. Okay, so you are going to use the formula of E equals to E naught over K. So which means that for you to find the original or the electric field without the electric, you just multiply your E. Here you get from this question, so you are going to get 25 power of 3 multiplied by K. So K is 3.4. Therefore, you are going to get your answer is 85 power of 3 volt per meter. Okay, so same as voltage between the plate. Okay, so once you remove the dielectric material, your V going to be increased. So you're going to use the formula of V equals to V naught over K. So for you to find the V naught, so V here is 100 multiplied by 3.4. So you are going to get here is 340 volt. Okay, and the last one going to be the energy stored in the capacitor. Okay, I'm going to use the formula, the same formula like question A, which is U equals to 1 over 2 CV square. So I already have C is 8.8 power of negative 9. Okay, and then I have the voltage, which is 340 square. Therefore, I'm going to get my answer here is 5.1 power of negative 4 joule. Okay. Okay, I think maybe you can actually realize that when you put the dielectric material, your energy is 1.5 power of negative 4 joule. But once you remove, your energy increased to 5.1. So where this extra energy comes from? Okay, the extra energy comes from is because to remove the dielectric material, definitely you need to have a very large energy, and that's the reason why you need energy is increased, because huge energy needed to remove the dielectric material. Okay, I think that's all for now. Okay, that is so we already finished chapter 5. So hopefully you understand. If you have any questions, feel free to ask. Okay, so assalamualaikum and goodbye.